One of the things that we learned in the previous video about the idea of principal components analysis is that we can compute the eigenvalues and eigenvectors of a matrix, specifically the eigenvalues and eigenvectors of the variance-covariance matrix, and we learned that the eigenvalues represent or can be used to represent what proportion or percentage of the overall variability in the data is explained by the eigenvector, the corresponding eigenvector in that one direction. So here we learned that the one eigenvector, 0.99, negative 0.14, which is approximately a line with a slope of 0.14, that along that line, that is where about 95.4% of the variability in the data is accounted for. Now, don't let your eyes deceive you. There's a lot of mathematics that comes into play here. It's not the line of best fit. This isn't linear regression. That's not the idea. It's trying to find the direction of maximal variation. Okay, so the direction where the greatest amount of change is. And now there's also change in the other direction, which we represented with this blue line, which is actually perpendicular to the green line. I want you to notice that if you actually take the dot product between these two eigenvectors, notice that you will get a dot product of 0. That's really valuable. It actually is known for this. We'll come back to that a little bit later. And so the direction here, according to this blue line, there is very little variability, only about 4.6% of the variability comes from the other direction, that orthogonal direction. Okay, I want to instill in you a little bit more intuition behind these concepts by looking at a couple of just toy data sets to show you how singular values might agree with what we actually see in the data. And I just want to still stick with 2 dimensions for now. Remember, this tool is used for dimensionality reduction. So ideally, this helps us understand larger data sets. Not so much that great for small data sets because, we can plot the data, we can observe it. So, by the way, the eigenvectors that we're referring to, they come from the variance-covariance matrix, not the original data matrix. Remember, we center the data about the origin by subtracting away the mean, and then we take that data once it's been recentered around the origin, and we find the eigenvalues and the covariance matrix of that data, and then we get our eigenvalues and eigenvectors. The square roots of each eigenvalue is sometimes referred to as a singular value, and this is tied to something called singular value decomposition. But I digress. So here's a toy data set, and I just want you to observe that when you plot this, there really isn't much going on here, right? It almost just looks like a dotted line. Connect the dots where it would be like a house on its side. Well, as you might guess, there really isn't a whole lot of like a dominant direction of variability, or at least not one that's strongly visible. If we compute the means and we find that the mean of the x values is 3, not surprisingly, because 3 is the middle value there, and then 2.8 is the average of these. Again, if we were to recenter these, I'm not going to be real precise here, but if we were to recenter these about the origin, it might look something like that. And then we get the variance-covariance matrix of that data, which would be given here. So notice that there's some spread variance in the x direction, some variance in the y direction, but ultimately, the eigenvalue that we get that is dominant is 4.06 compared to 2.14. Now I want you to notice that these eigenvalues are much closer together than they were in the example above, where the data really did have a strongly dominant direction. In fact, so much so that that eigenvalue consumed the majority of that variance that we observed. So in this particular example, we might say that, roughly 4 divided by, we'll just say 6.1. I guess if we're around 100 to the tenths, we should say 4.1. And then relative to the entire variance, the sum of these is going to be about 6.2 if we add 4.1 and 2.1. And 4.1 divided by 6.2 is like about 2/3. It's a little less than 2/3. This is about 66.1% of the variance is explained by the direction of the first eigenvector, of the first principal component. So if I were to plot that, and the reason I just kind of put these points here is if I were to plot that, that would say I would go over about -0.5. So in the x direction, just under -0.5, and then up almost 1. Okay, so that point right there, which that just corresponds to the eigenvector, would look something like this. Okay, now that doesn't necessarily have to fit with our intuition. If we fit a line to this, we might get a slope of about 0. Remember that the line here, and by the way, we could extend that through here as well, right? That's why we center it about the origin, because vectors are usually instantiated at the origin. And so that direction accounts for about 66% of the variation that we see. So if you look at the spread, if you were to project these down onto this line, then you would see that, they spread from, well, actually right about there to right about here, right? And if we look at the other direction that we have going on, the other direction is, again, notice orthogonal to that. So if I draw a perpendicular line in exactly the opposite direction, so perpendicular line here might look like that, and that's a right angle there, right? So something like this, perhaps. And that eigenvector, that direction, only accounts for, if you notice, a smaller portion of the variability. So that variability goes from there to there. Again, don't quote me on the exactness of this, but that's the other approximately 34% of the variability is in that direction. So what might we say as an interpretation? Well, we might say that for every, again, this is a recipe, the principal components are a recipe, the recipe, or the dominant recipe for 66% of the variation recipe would say that for every well, I'll start off with the 0.9 units of y, remove 0.4 units of x. Alternatively, you could say if you increase x by 0.4, you'll decrease y by 0.9. So you could either go back x and up y, or forward x, down y. All right, so that hopefully agrees with somewhat of our intuition. Again, maybe we might say, well, that's more 50-50, but mathematics, right? There's mathematics happening here. And here's a data set that I really hope drives the point home. These points are perfectly linear. In fact, this would be y equals 2x plus 1 if you were to plot this, plot the line that models this data. Well, notice that the means are provided here, the variance covariance matrix. So we have covariances and variances that just happen to be equal here. But look at this. The eigenvalues are 5 and 0, okay? And 5 and 0, let's think about this. Again, if we were to sort of center this at the origin, that data might look, somewhere along here like that, slope of 1. I guess it would look a little bit more like this, right? And what we're saying is that this eigenvector, which notice that the ratio of 0.7 to 0.7, that rise over run, here's your rise, here's your run, that is equal to 1. That's a slope of 1, right? So it just so happens that it exactly matches the slope because that is where all of the variation is. So if you take 5 out of 5 plus 0 and you convert it to a percentage, that's 100% of the variation in the direction of principal component number 1. By the way, principal component number 1 refers to the eigenvector for the dominant eigenvalue. So in the direction of principal component 1, which is, I'm just going to write as 1, 1, which is really, I'll say, equivalent to 0.7, meaning equivalent in the sense that they lie on the same line. They're not equal, obviously, because they have different components, but they are equivalent. They both represent eigenvectors, and that is where 100% of your variability is, right? It's between here and here. Now, it's always going to generate that orthogonal eigenvector, which would look, perpendicular to this, so perpendicular to this, but how much variability is on that line? Well, that's the other 0 out of the total, which is 0% of variation in the direction of PC2. 5 plus here. I get a little excited sometimes. So in the direction of PC2, which is the eigenvector negative 0.7, 0.7, or alternatively, you could say that's equivalent to negative 1, 1. So if you went back 1, up 1, you get a point. If you went forward 1, down 1, you get another point. And so basically that direction, right? It's exactly 0 because, well, the points don't spread in that direction at all. All the spread is in this one direction. So my goal here was to illustrate and to kind of compare and contrast our two toy data sets with our actual real-world toy patient data set. And now the question we want to answer is, well, how will this help us understand a correspondence among all of the variables that we are interested in explaining together? So I am going to come up with, in the next step, I'm going to have 4 principal components. I'm going to have 4 eigenvalues, 4 eigenvectors, because I'll have 4 variances, and my covariance matrix, variance covariance matrix will be 4 by 4. So what we've done, this groundwork, lays the foundation for analyzing principal components of larger systems as well.